Welcome to Math E102, the second distance learning course that I have taught. My name is Paul Bamberg, and I think I'll begin by telling you a little bit about myself and how I come to be teaching this subject in the Harvard Extension School. By training, I'm a physicist. I was a Harvard undergraduate between 1959 and 1963. In that era, the master of my house took pride in producing more Rhodes Scholars than either Princeton or Yale, so he recruited anyone with any academic talent to apply, talked me into it, and to my utter amazement, I got a Rhodes Scholarship, went off to Oxford, spent 4 years there, got a doctorate in theoretical physics, wrote back to Harvard. This was the Sputnik era, and jobs were easy to come by, and said, "Hi, remember me? I used to write the homework solutions for your introductory physics course. Fine, would you like an instructorship?" So I became an instructor in physics at Harvard, and I think I set some sort of record by teaching at Harvard in the physics department from 1967 to 1995 without getting tenure. How do you do that, you might ask? Well, the secret is you teach pre-med physics. That means if they let you go, someone else in the department has to teach pre-med physics, and that's unacceptable. So I stuck around. I got involved with the extension school first by teaching physics courses for the nuclear navy when I went down to Groton, Connecticut whenever the nuclear subs pulled in and ran discussion sections on electromagnetic theory. And I gradually rose through the ranks in the extension school until I became director of science instruction. In the 1980s, I started looking at what the rest of the world was doing, got into the speech recognition business, and was involved in the founding of a company called Dragon Systems, which produced the world's first large vocabulary speech recognizer. And for a long time, I was 3/4 time at Dragon, 3/4 time at Harvard. That was fine for a company of 12 people. When we got to 250, I found I could no longer say, no, I really can't come to a board of directors meeting at 9:30 on Thursday, because that's when Physics 1 meets, and I have to give my lecture. So, somewhat reluctantly, I retired from Harvard. I carry a retiree ID card, and became a full-time captain of industry, along with your fellow student Jay Tucker here. We produced some great pieces of software that did voice-to-voice translation in Bosnia and so on. And eventually, we decided it was time to cash in. We sold our company for a lot. A lot of stock, it turned out, in a company that was about a year ahead of Enron in the creating a creative accounting business. Within 4 months after the acquisition, the company that had bought us was bankrupt, and I wasn't enamored of their management style. So I retired from high-tech industry, let it be known I was available. What do you know? 2 weeks later, I've got an offer from the Harvard Math Department. Now, this is weird. I have never taken a graduate-level course in mathematics in my life. I had co-taught a lot of courses while I was in the physics department with senior faculty in math, helped produce a very nice 2-volume textbook, and had a good reputation as a teacher, but I didn't really expect to get an offer for a position that I assume 100 mathematicians in the country would give their eye teeth for. So I accepted it, and they said, well, you teach non-Euclidean geometry. I thought, but did not say, yeah, I've always wanted to know non-Euclidean geometry. I'll do that. Will you teach probability? Well, you know, that's my lifeblood, because the first real course I did in the physics department was when the chairman said, X, who's supposed to be teaching probability, has announced who's going to be teaching statistical mechanics, has announced he can't be at Harvard this term. Could you teach it? I didn't say, you know, that's the only major course I didn't take when I was an undergraduate. I said, sure, fine. I became an expert at that. Speech recognition is all based on probability theory. So this was a subject I'd been working with for a long time, and I taught a course in probability in the college and thought, this is so much fun, I might as well do it in the extension school, which I did for the first time last spring. I think everyone had a good time and learned a lot. And this year I've decided to take the plunge and go into distance learning. You have a classmate who's serving in the military in Iraq, plus a handful of other people who can't easily drive to Cambridge. and we're going to put all the lectures on video, which means that you, as well as they, will be able to see them online. Let me start by going through some of the nuts and bolts of this course. And if you pull out your handouts, if you're a late arrival, you should just walk up here and grab one. First, please, if you address me as Paul. I am not a professor. And if you address me as doctor, you're rubbing in the fact that I'm not a professor. So Paul is the right way to do it. I have two offices. One, rather inconvenient, is in the Science Center with the inconvenient office hours of noon to 1 p.m. I also have a faculty apartment in Quincy House, and I'm happy to meet with extension students before work. I've listed 8 o'clock, but from time to time I've met with people at 7 o'clock. Given enough advance notice, I'll be happy to do that. Or if you live out in the western suburbs and want to come chat with me on my house in Marlborough, that's also fine. My course assistant is one of my undergraduate probability students. I think he's going to be a great teacher, and he's also essential to casino night because he runs the best craps table at Harvard. His name is Chris Yetter. Like many mathematicians, he's a musician too. He has orchestra rehearsals on Tuesday nights. So he'll be teaching sections before class, but he won't be here at class. So I have to pick up the homework when you start turning it in and give it to him. I deliberately decided to keep the prerequisites for this course low in hopes of attracting lots of high school students. This has clearly not worked, but it still makes for an interesting course. This is all going to be discrete probability. We will get into some mildly advanced topics, but we will never use calculus. We'll have to use infinite series from time to time, but by and large, I will develop that topic as we need it. If you can sum a geometric series, you're ahead of the game, and I will take it from there. The textbook is Elementary Probability by Sturzacher. There should be plenty of copies in the coop. You can also get it from Amazon.com. This book got mixed reviews from last year's students, but it's the only one I can find that covers all the relevant topics, and I think it's got some really nifty examples in it. You'll be doing homework, of course, and for those of you who come to class, this is fairly straightforward. At the end of your packet, you will find the first 4 homework assignments, which will take us up to the first quiz. For those of you who are watching this lecture on video, you'll want to know that you can submit your homework by scanning it and emailing it. You can submit it by faxing it. And in either case, your deadline is an hour earlier than everyone else's. You folks who are here in the room have to turn in your homework when you come to class at 7:35, but I figure many of you hop into the car at 6:30 to 6:45, so the folks who are just sitting at their computers are expected to get it in at 6:35. Chris will be teaching the section from 5:30 to 6:30, which means that right after section, he can pick up the distance homework. The sections are going to meet from 5:30 to 6:30, not in this building where there are no classrooms available at that time, but at 1 Story Street. Story Street is right off Brattle Street. It's on the other side of Brattle Street. You go up to the 2nd floor, and there's a nice little section room in which you can meet. Chris will be willing to give broad hints about the homework. This leaves you an hour in which either to eat dinner or incorporate the hints into your homework, but it means you can do everything with 1 trip to Harvard per week, which last year's students decided was the most important criterion. The second section we're going to run in cyberspace. I picked Sunday night as a time that people are likely to be free, 8 to 9 p.m. Eastern Time. If you're in Iraq, you'll have to calculate exactly what that means. And what we have done is to create a bulletin board. This bulletin board will be active all week, and if you put a question on it on Wednesday, there's a good chance that Chris or I will see it on Thursday or Friday and give you an answer. But on Sunday night, 8 to 9 p.m., one or both of us will be online, your classmates will be online, and you're likely to get an instant response to almost anything you post. Jay, we did this in computer courses, didn't we? And
not instantly, but we certainly had bulletin boards which were monitored quite regularly.
Yeah. So if you, one possibly unattractive feature of this is if you read the bulletin boards, there are going to be an awful lot of spoilers there that tell you how to do the homework problems, and I've decided not to worry about that. I would say, in accordance with bulletin board convention, if you pretty much give away the whole answer to a homework problem, you should write something like, spoiler, solution to problem number 2, and then the scrupulous will not read it. One thing I found out about this bulletin board is you can't even see it until you log in. This is a little more security than I'm accustomed to. So you have to go through the registration procedure. You'll get an email, you get a password, and then you will see the bulletin board for this course. Up to that point, you will only see the bulletin boards for 5 courses last year that didn't have such security procedures in place. We're going to have 2 quizzes and 1 final exam. Last year we had 2 40-minute quizzes. It was clear that good students in the class needed 55 or 60 minutes for what I regarded as a reasonable 40-minute quiz, so I kept extending the time. This year I'm just going to make it official. The quizzes will be an hour in length, typically 4 questions. Some of you will mess them up because you haven't taken math exams in 15 years, and so we will have a repeat quiz typically the Sunday of the week after the original quiz. The catch with the repeat quiz is your score cannot exceed 80% on that. So you can't get a super score, just a reasonable score on the makeup quiz. For those of you who are distance learners, you should consult the distance learning link that's in the syllabus, and you'll find out how you can arrange in advance to have a properly proctored version of this exam administered to you. The exam folks were very good sports about these repeat quizzes. I thought it was very generous of them to say, yeah, I guess we're willing to get proctors for 4 quizzes for 1 student if necessary. But when I said, and last year, you know, we gave everyone 2 shots at the final exam, they pretty much drew the line. So the deal on the final exam is a week before the final exam, there's not going to be a class. I'm going to email everyone an exam equivalent to the real final exam, perhaps the one I gave last year, and if you want to try, you can sit down with no references, see how well you can do on it in 2 hours and 15 minutes or 2.5 hours, because they have said, yeah, you can give your students 2 hours and 15 minutes to give a 2-hour exam. We won't object to that. And then the real final will be the next week. But if you get 100% on the practice exam and 60% on the real final, the 60% counts, unfortunately. One of the things that I'm fairly passionate about is the interaction between computing and mathematics. And with that in mind, I have created 2 fairly nifty programming assignments for this course. Those of you who are in master's programs in information technology, who already have learned to program through the extension school or who do it for a living, are expected to do these assignments, which means I'll be a bit disappointed if you don't, but I won't enforce it. The rest of you are welcome to try. I think they're challenging enough so that if you have no programming background, you won't be able to figure out how to do them. But apart from that, it's a level playing field because I'm doing them in PHP, a very nice scripting language that writes web pages. If you know C++, Java, Perl, Python, or even, heaven forbid, BASIC, you'll be able to catch on to this fairly quickly. I'm going to provide highly explicit instructions about how to do the HTML, good hints about how to do the mathematics, and last year we got some very nice programs out of about 1/3 of the class. This is by no means required. In a couple of weeks I will have some CDs which will let you install PHP and an Apache server and everything that goes with it on your PC. You do this using your own PC as both client and server. When it's all done, one way to submit it is just make sure that I can look at your server, send me an email, say, Paul, assignment 1 is done. I type in the URL that you give me, look at it running on your machine, and if it looks good and is correct, you get full credit. Of course, I can't see when I'm looking at the program running on your computer whether your formatting is clean or whether you've documented your code, so I'm not going to care about that. If it's correct and looks nice, you'll get full credit. So in adding up the grades, we'll have 40 points worth of homework. I'll scale the better quiz up to 25 points, the worst quiz down to 15 points. The final exam would count 50. If you do the programming assignment, you get what you get. There are all sorts of credit and extra credit, but if you get 18 points out of that, we'll add 18 points to both the numerator and denominator in your grade. If you're getting 100% and everything else, this is totally useless. But if you're getting 70%, this is a nice boost. And then because I decided last year I was really impressed with the people who'd taken the time to do this programming stuff, I'll take 10% of your programming grade and just throw it in as extra credit. There's one other opportunity for extra credit, and this is one that I think the distance students are going to have to miss out on. In December, you'll get to put your probability into practice. We'll have a casino night in the Quincy House Senior Common Room. You show up dressed for class, you get $300 in play money. Show up in a tux, you get $500 in play money. Show up with a guest who is wearing a floor-length dress and high heels. The two of you get $1,000 in play money. My wife, the Wonder Shopper, has purchased a blackjack table, a craps table felt, and a rather nice roulette wheel. I have Harvard undergraduates who are expert at running these, and we will sort of do the romantic ideal of the casino with James Bond themes playing in the background. At the end of the evening, the 5 people in the class who, with their guests, have the greatest winnings or perhaps the smallest losses if it's a good night for the house will get 5, 4, 3, 2, and 1 points of extra credit respectively. And after I add all this up, I'll use my grade conversion table in the syllabus. As far as I'm concerned, if you can get 92% of these points, you get an A. If everyone in the class gets 92%, everyone gets an A, and that's our goal. If nobody ever comes back to class and you all decide to stake it all on the final, you could all get Ds. I'll do that too. Last year the grades turned out fairly reasonably, and I think people felt you had to be pretty clever to get a straight A. Really hard work would give you a good shot at an A-. And there were some people who said, whew, I made it through with a B+. I wasn't sure I was going to be able to do that. I put a list of topics in here which you can browse at your leisure. So that's how the course is going to run. People in the classroom have some questions about this? It'd be nice to have at least one question. Anna, do you have any advice for people taking a course from me? Anna took my geometry course last spring.
Don't leave the homework to the last minute.
That's very good advice. Thank you. Okay, so we can move on. The next thing in the packet after the syllabus is relevant mainly for the distance learners. It's a fax cover sheet to use when you fax in your homework. But some of you folks may be hybrid distance learners. How many of you characterized yourselves as hybrid distance when filling out the form? Okay, for you, here's what I'd like to do. I really want you to be in class tonight when the first quiz is given and when the second quiz is given, and all the copies of the handouts, which everyone who's arrived should get. Walk up here and pick one up if you don't have one. All the copies of the handouts will be given out on those nights. On other nights, you have the option of submitting your homework by fax or email, staying home, and 24 to 48 hours after the lecture, watching it online. And all of you have the option of watching the lecture online. This should be a real boost from distance learning. If you say, I really didn't understand the Monty Hall problem the way he explained it, you can go back, look at the table of contents, find the timestamp for the Monty Hall problem, and review that part of the lecture. Okay, let's get going with some content. I'm going to start out with topic number 1, and that's the timestamp, probability by symmetry. Because in fact, mathematicians were doing probabilistic calculations for a couple of centuries before this subject was formalized, And I suspect that human beings were doing this sort of calculation for thousands of years before it's formalized, because it looks to me as though people are sort of wired for probability. They make some mistakes, but have some reasonable ideas. So let's think about some things that you might encounter on casino night. Someone takes a deck of cards, shuffles it. Now, when I say shuffles it, what I mean is I'm assuming that this deck is shuffled in such a way that any of the 52 factorial possible arrangements of the cards is equally likely. It's been shown that with 7 perfect shuffles, you get fairly close to that. With 6, in fact, you don't do very well. But that's the assumption we're going to make about this deck. And then we start playing blackjack, and let's just imagine the dealer starts out. Have I got the mic back in the right place? Oh, the dealer gives himself a card face down, and you make some decisions based on this. So let's think about some simple questions you might ask. What's the probability that that card's a spade? Someone?
1 out of 0.
Why do you say 0?
Because we saw it.
Okay, so you're saying the conditional probability, given that I saw a red flash that it was a spade, is 0. That's correct. Someone who didn't see the card at all, what's your answer?
1 and 4.
That's right. And what's your reasoning?
There's 4 suits.
Okay.
Divided equally.
There's 4 suits divided equally. Or alternatively, there are 52 cards in the deck, 13 of them are spades.
Yeah,
so this is the way people do elementary estimates of probability. You've got a bunch of alternatives, and you say they're all equally likely. Any card in the deck is equally likely to have been that top card. And since all I'm interested in is a spade, 13 of them are spades, that gives us 13 out of 52. So we can say we've got 13 spades out of 52 cards. And the key theoretical part of this is in the denominator. You're saying there are 52 alternatives, and you're assuming they're all equally likely because you don't have any basis for assuming anything any more interesting about it. Let's try a couple of others. If the dealer has an ace, you're likely to be in a comparatively weak position. What's the probability that this card is an ace? Yes?
1 out of 13.
1 out of 13, and your reasoning?
There are 4 aces in the deck.
Yeah, so we got 4 aces. Out of 52 cards. And of course, people have been very scrupulous about reducing these fractions to lowest terms, but in some ways, they're easier to visualize if you leave the 52 in the denominator. What's the probability that it's a 10-point card, which means a 10, jack, queen, or king?
116.
16 over 52.
16 out of 52, because there are 16 such cards, 4 in each suit. And there what you're saying, and actually what you're saying in all these cases, is for a specific card, like the Queen of Spades, the answer is 1 out of 52. But if there's a set of these cards that will do the job, I will just add together these equal probabilities. So this is a very simple sort of calculation. Same principle applies to roulette. Turns out the only sort of roulette wheel you can buy in this country is the so-called American roulette wheel, which has both a 0 and a double 0 on it. This is unsatisfactory because roulette then has such lousy odds compared with blackjack or craps that no sane person would play it. So what we do at casino night is we say double zeros just don't count. We'll play as if it were a European wheel. But if it's an American roulette wheel, you look at it and you see it, and there are these various slots with numbers on them, 38 of them. And you look at the wheel and you say, this looks pretty well balanced. They all look the same width. I really can't see any reason that the ball is any more likely to land in the slot numbered 3 than in the slot numbered 17. I gather there are people who carefully study roulette wheels and discover that's not quite so, and in extreme cases can actually make money out of roulette, but that's not an unreasonable assumption. And so you have the opportunity to bet on the proposition that the ball ends up in an odd-numbered slot, in something numbered 1, 3, or 5. What's your estimate of the probability for that?
3 out of 38.
How many out of 38?
3? 1, 3, or 5?
No, I'm saying any odd number. I was just giving those as examples.
18 out of
Is
30.
it 14? How does the wheel...
There are numbers 1 through 36.
38.
And then there's 0 and double 0. How many odd numbers have we got?
18.
18 odd numbers. So we get 18
38.
out of 38. Not particularly good odds, but that's the correct estimate. When you play roulette, you discover you can make other bets, like the ball coming to rest in the range 1 through 6. What's the probability of that?
6 out of 38.
6 out of 38, okay. You can make a bet by putting a chip in between 29 and 30, and you win if it's 29 or 30. The probability of that is
2 and 38.
2 out of 38. Nothing really to this. So people have been doing probability this way for millennia, and mathematicians, including some of the world's best, have been doing it for centuries. And one of the things we want to do in this course is to go beyond that naive view of probability. I've mentioned craps here, but we'll come back to craps, so I will skip the topic on craps in the lecture outline and go on to something a little bit different. This is topic 2, probability by experiment, just to show you that this isn't the whole story. Okay, Jay.
Yes.
What's your guess of the probability that if I pick someone at random in this class and say, have you ever taken a math class in the Harvard Extension School before, the answer will be yes.
Say 1 of 3.
1 in 3. Okay? Have you ever taken a math course in the probability?
Nope.
No. Well, Jay said it was only 1 in 3, so you say Jay's a pretty good guesser. But the fact is, most people will give an answer to that question. And Jay isn't saying, you know, I know that there are 3,000 students enrolled in extension courses and that 1,050 of them have taken math courses here before, and I'll round that off. Jay's just making a guess. This is called subjective probability, and a lot of people, myself included, feel that this is a perfectly reasonable way to estimate probabilities, even when you can't identify a set of equally likely alternatives. Okay, now let's do this a little better. I'll go down this row and ask everyone the question, have you taken a math course in the extension school before? Say yes or no. Your no?
Yes.
Yes?
No.
No.
A yes and 2 no's? A yes and 3 no's?
Yes.
2 yeses, 3 no's? 3 and 3?
No.
3 and 4?
Yes.
4 and 4?
Yes.
5 and 4? 5 and 5. Okay.
No.
What's your estimate? No, no.
Oh.
I've asked 10.
No.
Now I'm about to ask someone else. But before I ask someone else, what's your estimate of the probability that the next person I ask will answer yes? Well, I just asked 10 people, and 5 of them said yes, and 5 said no. So a reasonable thing would be to say, well, roughly 1/2. And that's another way of estimating probability. You do experiments, and then you use the frequency of occurrence of the desired outcome as your probability estimate. And if I asked 100 people and 50 said yes, then you'd be a little more confident in saying 1/2. So that's another aspect of probability. But there's a catch to this. Suppose instead of asking the question, have you ever taken a math course in the Harvard Extension School before, the question I was asking was, does your birthday fall in the 4 months between February and May inclusive? And 6 out of 10 people said yes. What's your estimate for the answer, for the probability that the next person will answer yes? I repeat this. So the question is, does your birthday fall in the 4 months of the year between February and May? I asked 10 people and 6 of them answer yes, and you have to bet on whether the next person is going to answer yes. What do you think is the probability that the next person will answer yes?
1/3.
1/3, because you know a whole lot. You know that people are born fairly uniformly throughout the year, and therefore that knowledge overrides the experimental evidence. So now you're seeing this subject is a little bit more complicated than just counting cards in a deck. I'm talking now about the first chapter in our textbook, which is numbered Chapter 0, which was actually added in the current edition to sort of introduce the topic. And the next thing I'd like to talk about a little bit is the connection. Ooh, I'm going to have to bring a thing of blackboard spray if we're going to be able to read this for a long time. I'll do my best. About how you can talk about probability in terms of a payoff. So let's think about craps for a while. Since you may not all have misspent your childhood playing craps, I'll have to tell you a little bit about craps. So the way craps works is the shooter rolls the dice. If the shooter rolls a 7 or 11, he or she wins. If the shooter rolls a 2, 3, or 12, he or she craps out and loses. And if the shooter rolls anything else, the shooter establishes a point. And let's say, for the sake of argument, that the point is a 4. And let's calculate right off the bat the probability of rolling a 4 with 2 dice. Who can suggest one way that the numbers on the 2 dice can roll up, can come up so as to give you a 4?
1 and 3.
1 and 3. Another way? 3 and 1. And the third way? 3 and 2. So there are 3 ways of getting a total of 4. 3 out of 36 is 1 out of 12. Now the rules of craps say that if the shooter rolls a 4, then he or she wins. If the shooter rolls a 7, he or she loses. And for a 7, you have 1 and 5. You have, you have 1 and 6, 2 and 5, and so on. There are 6 possibilities in all. You can have any of the 6 numbers on one die, and the one that matches with it, the total 7. So the probability of getting a 7 is 6 out of 36, which is 1/6. And the probability of neither is 1 minus 1/6 minus 1/12, which is 3/4. Yeah, it's a 6. So as the game goes on, each time the shooter rolls the die, there's 1 chance in 12 of rolling a 4 and winning, 1 chance in 6 of rolling a 7 and losing, and the rest of the time, which will happen with probability 3/4, the game will continue. And a question that's worth asking is, what's it worth betting on this? Let's suppose, for the sake of argument, if the shooter makes the point, you win $12. This will make the numbers come out nice and round. And a question you have to ask is, what is a fair amount to pay for making this bet?
What does makes the point mean?
Makes the point means rolls a 4.
4 or 7.
Oh, 4.
Now, there are actually lots of ways of doing this problem, and I'll do roughly 1 per week for the first 3 or 4 weeks of the course. But the way I want to approach it this week, you'll see why in a minute, is to say, what is the amount X that you are willing to pay if the deal is, if the shooter rolls a 4, you get $12 back. If the shooter rolls a 7, you get $0 back. Otherwise, your $4 is refunded, and you get to bet it again. In practice, the money just stays on the table when you're playing craps. So let's think about that. You can say that what you might get out of this game is $12 multiplied by the probability of rolling a 4. Fair enough? Plus $0 times the probability of rolling a 7 plus $4, plus X dollars, your bet back, times the probability that neither a 4 nor a 7 is rolled, and that if the amount you expect to get back is equal to the amount you bet, it's a fair game. Okay? I have introduced here the concept of expectation, which will show up later in the course, but I want to introduce it now in order to show you that this concept provides an alternative way of getting at probability. Okay, let's do this calculation, and those of you who think you know the answer will discover you've got it right. 12 times P4 is 1. This is 0. This is 3/4 X. That has to be equal to X, and therefore, oh wait, I forget where the camera is. 1 equals 1/4 X, or X equals $4. So if you have to pay $4 for this bet, it's a fair game. If you could pay $3 and make it and play this game, it's a really good deal. If you have to pay $4.50 or $5 to make this bet, it's a losing proposition. Okay, everyone see, probability estimates provide you with a way of deciding whether or not a game has a fair playoff. Now let's turn this around. We'll do this first in a context where we can estimate the probability. The protagonists are Sam Adams and Peter Stuyvesant, for reasons you'll see in a minute, and they're going to make a bet on what card is turned up for this deck. And the deal, as I have said in the notes, is Sam Adams puts up $3, Peter Stuyvesant puts up $10. If the card that comes up is a face card, Sam gets all the money that was put up. If the card that comes up is not a face card, then Peter gets all the money. And let's figure out whether this is a fair bet or not. And we can decide this by calculating Sam's expectation. Sam wins $13, but Sam wins this $13 only if a face card comes up. What's the probability of that?
3 of 13.
3 out of 13. And Peter has an expectation of $13 times 10/13, which is $10. So they both say this is a fair game. Okay. They were betting on the turn of a card. This is something that lends itself to a repeatable experiment. You can shuffle the deck, do this over and over and over again, and if your shuffler is any good, you will discover that jacks, queens, and kings come up 3/13 of the time. But now they're going to bet on baseball. So I'm now talking about topic 4, fair price and probability, and they're going to make a bet on who wins the American League East. And they argue about it a bit, and they finally decide that a reasonable friendly wager is this. Sam puts $15 into the pool. Peter puts up $10. And Sam wins the 25 if the Red Sox win. And Peter wins this if the Yankees win. So assume that these two friends have decided this is a fair bet. What's Sam's estimate of the probability that the Red Sox will win the AL East?
60%.
60%, because he's willing to put up 60% of the pool. And so this implies that the probability that the Red Sox win is 60%. And therefore, it's not unreasonable to say that anytime you have a situation that people are willing to bet on, it's reasonable to talk about probabilities, because when people agree on fair odds, they're agreeing on an estimate of the probability, even for something that's a one-time occurrence. You know, next year the Red Sox and the Yankees will have different personnel. It won't be the same repeatable experiment like shuffling a deck of cards and dealing from it. Now let's think about combining probabilities. So you've got a friend who thinks that the Red Sox have a 60% chance of winning the AL East, and this person's also interested in international politics and says, I think there's one chance in 4 that the Iraqis are going to reject that constitution. And you say, what do you think is the probability that the Red Sox will win the AL East and the Iraqis will reject that constitution? So 60% on the Red Sox winning, 1 in 4 on the Constitution being shot down. What do you think is the probability that both will happen?
0.6 times 0.25.
0.6 times 0.25, or 15%. Now, before discussing the hidden implication here, I think I'll do the other example first. Here's another similar situation. You got a friend who's really into financial stuff, and she says, you know, I think there's 3 chances in 10 that next year average corporate profits are going to be twice what they are today. Like, that's interesting. What do you think about the Dow? Well, I think there's 1 chance in 3 that the Dow will finally make it above 11,000. You think, well, what's the probability that both these will happen? Oh, I know how to do this sort of problem. 0.3 for the corporate profits doubling times 1/3 for the Dow going above 11,000. I bet there's 1 chance in 10 that both those things will happen. Someone want to tell me why that argument is total rubbish? Yes?
Because the two things are not independent.
Very good. So you've used the technical term. Those are not independent events. If corporate profits double, the probability given that the Dow will go above 11,000 is pretty close to 1. Whereas in this case, it's hard to imagine some Iraqi walking down to the polling place and saying, well, I was going to vote for this Constitution, but I'm so shocked that the Yankees beat out the Red Sox that I'm going to vote against it to show how much I hate the Yankees. So these are independent events, and you know they're independent because of your knowledge of the way the world works. And similarly, these are not independent events. You know about that if you have some rudimentary knowledge of finance. So this business of estimating what happens when you combine probabilities is not trivial, and it's something we've got to start theorizing about. Okay, now I'm going to get a little bit formal, and I'm going to start on topic 5 in the outline, which is notation to combine sets. Now, this was, until yesterday, notation for combining sets. But I figured there'd be some tricks to distance learning, and the one I hadn't anticipated was that when I submit the table of contents for this lecture, no title can have more than 26 characters in it. So my wife went through all the outlines. She counted letters, including spaces, marked all the ones that had more than 26 letters, and I shortened them without attempting not to change the meaning, so they will all fit. This is notation that you may be familiar with. You may not be familiar with it, but it doesn't really matter because you can learn about it for the first time tonight and do just fine. I'm not going to copy these things onto the whiteboard because of shortage of space, but if you look at the notes, you'll see I've defined some subsets of the U.S. population. And by the way, when we're talking about probability and subsets and events, we're always talking about subsets of some well-defined universal set. We're not talking about subsets of everything or subsets of all concepts or something like that. Here we're talking about subsets of the U.S. population. And there are actresses, there are actors, singers, basses, women, waitstaff. I've given them names. And what I want to do now is just introduce or review some mathematical notation for making new sets out of old. So given these 6 sets, A through F, if I ask you how you would specify the set of thespians, anyone know enough set theory to give me a notation that represents the subset of thespians? Yes, please.
A intersects E?
No, A intersects B would mean someone who is both an actor and an actress. Let's try again.
A union B?
A union B. You got it right. So thespians.
Some singers are actors too.
That doesn't really matter because if singers are also actors, if you take everyone who is an actor or an actress, that gives you all the thespians. Some of them may also be singers, but that doesn't add anything to it. That is, if some singers are actors, and I take the union of this with the singers, that doesn't enlarge the set any. So this is the simplest correct answer. Okay, let's try introducing some more notation. Waitresses. How do I write the set of waitresses? Yes?
Intersection F.
Okay, the set of waitresses is E intersection F. So for those of you who haven't seen this notation before, this means you're a thespian. If you're an actor or an actress, this means you're a waitress only if you are both a woman and a waitstaff person. Okay, let's try one that's using different notation. How might we express the set of men in the U.S. population?
Not E.
Not E. Yep. And the notation our book uses for this is an a superscript C for complement. So E sub C means all the entities that are in the U.S. population, but that are not women. That's men. And finally, one that's rather tricky, tenors.
E complement union C.
E complement. What are you doing with E complement?
No, D complement.
I've got E complement. Okay, E complement is men.
No, D complement.
D. Bases.
No. Good guess, but an alto is not a bass.
Oh, yeah.
So we've got a subset of that, but that won't do it. E complement's a good start. Who can see how to finish this out? E complement gives us men. Okay, now how are we going to make basses? Yes?
Well, you intersected it with singers and
We'll intersect that with C. Very good. Okay, so that gives us all male singers. And now, once we've got all male singers, how do we get it down to the tenors?
Take out the bases.
We take out the bases, and the notation for that is take away D. So now you've seen all the terminology of set notation: union, intersection, complement, and set difference. And this provides us with a way of making new sets out of old. And one of the things we need to do now is to come up with rules that make probabilities for new sets out of probabilities for old sets. Question?
You can write the parenthesis also as C difference D, right? C difference E. Sorry, excuse me.
Yes, this is not the only way of writing this, and I'm going to be getting into some generalized identities, so I won't follow up specifically on that, but you're very definitely on the right track. Okay, I think we can do one more before we take a break. So I will now tell you about something you're very likely to have seen, namely Venn diagrams. Now, Venn diagrams don't prove anything. People think Venn diagrams prove things, but they're really a mental crutch. They're like diagrams you draw in Euclidean geometry. If someone says, show that the base angles of an isosceles triangle are equal, you draw an isosceles triangle. You say, yeah, those angles look pretty much the same. That doesn't prove anything, but frequently the diagram gives you great insight into how to prove the theorem, and the same thing is true of these Venn diagrams. Basically, when you draw Venn diagrams, you are using subsets of the set of points on this whiteboard, and it's an interesting thing. These are rather complicated sets. They're infinite sets. They're uncountably infinite sets. Lots of times, we'll just be working with sets that have a finite number of elements in them. So the Venn diagram is dealing with a rather complicated sort of set, but it usually gives you good insight. So let's try one. Someone says, convince me that if I take the set A intersect B and form its union with the set A intersect C, and notice I need the parentheses here in order to make this ambiguous. This is the same thing that I would get if I formed the set B union C and took its intersection with A. This is an example of a set theoretic identity, and while it's not a proof, a very reasonable first step in dealing with this is to draw a picture to illustrate it. So here's what a Venn diagram looks like. I'll say B is the set. It's the set of points that lie inside that circle. C is a set. It's the set of points that lie inside that circle. And maybe I will change colors on this one. And there's A. Now, the great thing about these Venn diagrams is it makes it very easy to identify the sets that are alluded to here. Where would I find, for example, A intersect B? You can't say, can you? I'm sorry. And since I don't have waivers, I can't ask any of you to come up to the blackboard and show me this. But there's A intersect B. It's the set of points that lie within the B circle and also lie within the A circle. Okay, let's try in green. A intersect C. And now you can see on the diagram, I can actually try giving it a squiggly outline, the set of all points that lie either in this or in that. And then you say, look at the right-hand side. First, I take the union of B and C. That's the point that lies in one or the other of these circles or both. And all this identity is saying is the set of points that I have identified is the same set that both lies in circle A and lies in the union of B and C. And I see that I've identified the same set of points on the blackboard. The only real peril in Venn diagrams is that you might unwittingly draw a special case. For example, if you draw a Venn diagram like this, you can be led to wrong conclusions because the set A intersect B intersect C is empty. And you might write something down where you should have a term involving the intersection of A, B, and C, but you look at this diagram, you don't see any points that belong to all three sets, and so you jump to the wrong conclusion. What's the right way to prove something like this? Well, I'll tell you what it is, but it's deadly dull to do, and I suspect only a philosopher can do it right. The way you're supposed to prove something like this, well, maybe one of you can tell me. How do you prove that two sets are equal? Yes?
So they are subsets of each other.
Yes, very good. You show that each is a subset of the other. So to show that A equals B, you should show that two things happen. A is a subset of B, and also that B is a subset of A, and therefore you might reason like this. I'm not going to write it out. I've written it out in my notes, but it's not worth transcribing on the board. Suppose that something either lies in the intersection of A and B or lies in the intersection of A and C. Well, then it surely lies in A, and it also lies in either B or C. So if something belongs to this set, it belongs to that set. Then, to be rigorous, you have to turn the argument around and say, well, suppose something lies both in A and in the union of B or C. That can happen only if it either lies in both A and B or if it lies in both A and C. So in that sense, you have turned union and intersection to if-then, and you've sort of reduced set theory to logic. Such an argument is better than a Venn diagram, but I don't want to be very fussy about how we prove these things. I only want to point out that on occasion you will have to show that two sets are equal, and the not quite so obvious thing is you have to show that each is a subset of the other. So I got 5 minutes left, okay. Okay, with 5 minutes, I will say a little bit about events and sample spaces. And now I'm moving on to chapter 1 in the textbook, which really was the first chapter in the previous edition. So you've had this little introduction to probability theory, and now you can start out on a rather more formal version of it. So we're talking about experiments, where by experiment I'm really thinking about something you can do over and over and over again, like shuffling a deck of cards and looking at the top card, or rolling a red die, a white die, and a blue die and looking at the numbers that show up on them. I'm talking about a sample space omega, which is the set of all outcomes of this experiment. If I'm dealing one card off a deck, for example, the sample space will consist of the 2 of clubs, the 3 of clubs, the 4 of clubs, on up through the queen of spades, the king of spades, and the ace of spades. And then the easy thing to talk about is an individual outcome. Example, I deal the ace of spades, and early on you were quite correctly identifying individual outcomes that plausibly all were equally likely, and therefore which each had a probability equal to 1 over the number of outcomes. And finally, we have events. An event might be I turn up a heart, or I turn up a 10-point card, or I turn up an ace, or I turn up a spade. Events correspond to sets of outcomes, and these correspond to subsets of the sample space. And at the risk of complicating things, since I have only 2 minutes, I'm going to stop now. We'll take a break for, let's take a break till 8:45, and then I will resume this topic and we'll figure out how to deal with this in the table of contents. A couple of examples. First, a straightforward and rather mundane one. So the experiment will be roll 3 dice, one of them red, one of them white, and one of them blue. Who can give an example of an individual outcome in this experiment? Yes?
There's a 1 in 6 chance the red die will come up with a 1. Is that what you were looking for?
It's close, but there are 2 things I take slight issue with. You said a red die will come up with a 1, and you said the probability is 1/6. In specifying an outcome, you don't need to talk about the probability. So saying that the red die has a 1 on it is fine, but so far you've got an event, because there are all sorts of things that can happen on white and blue. So that's not an individual outcome.
They all come up 3s.
They all come up 3s. Okay, that's an individual outcome. You've specified everything about it. And Jerry, what's your estimate of the probability for that?
1 out of 256. 216,
Thank
sorry.
you. Second try.
I was thinking binary.
I almost wrote it wrong. So, the nice thing about an individual outcome is that in a simple case like this, you can, just by counting, estimate the probability of an individual outcome occurring. Now, you have already specified one event. Your event is the number showing on the red die is a 1. You want to estimate the probability of your event?
1 in 6.
Okay, exactly right. So your event is 1, anything, anything. And you did a shortcut calculation to get 1 in 6, but if we're doing strictly counting, we should say there are 36 ways for this to happen out of 216, presumably equally likely individual outcomes, which comes out to 1/6. Someone want to specify another event of a sort that's very frequently talked about when people are rolling dice?
Total 7.
You roll a 7. That is, when the 3 dice are added up, the sum is a 7. And with a bit of effort, at the end of the course, you will discover an extraordinarily clever way of doing this. But right now, by brute force counting, you can look at these 216 possible individual outcomes, count how many of them lead to 7. At the end of the course, I won't tell you how you can do this. You will be able to answer the question, if you roll 10 dice, what is the probability that the sum of the numbers showing is a 26? And there's a way of doing this involving just 3 binomial coefficients. You can actually calculate it, but you'll have to learn about generating functions to do that. At the moment, we have no subtlety. We can do it only by brute force. Okay, let's think about something that is a little less mechanical. So the experiment is choose a member of the U.S. House of Representatives. You might say, we'll pick the next person who speaks or the next person who walks into the house chamber or something like that. An example of an individual outcome.
Tom delay.
Tom DeLay, exactly the man I had in mind. Yes.
I was thinking the next one that gets indicted.
Oh, wait a minute. You're ahead of me. How do you spell it? Well, something like that.
Capital D.
Capital D, okay. And in this case, if you're doing next person to speak, next person to walk in the door, equally likely is not a reasonable assumption. There might be someone who spends all his time back in his home district. If, however, you put these folks on playing cards and had the U.S. House playing cards and dealt one, then they'd be equally likely. Okay, examples of events in this context. Now, what I mean by an event is something that may be more complicated than an individual outcome, but it's a subset of the sample space, a subset of the set of individual outcomes, and therefore it's some set of House members characterized in an interesting way. Republican, okay. So an example of an event is what's the probability that you get a Republican? What's the probability that you pick someone who is under indictment? I had one other example. Someone who's in the leadership. And it may well be that the intersection of these three events is this individual outcome. So I'm using the language individual, outcome, and event, but I'm really talking about subsets of a given set. Probability is a branch of mathematics that deals with subsets of a set in an organized way. Okay, that finishes topic 7, and we're now ready to go on to topic 8, which is called event spaces. And now we're going to get a little bit fancier. Because, as one of your classmates just did, the temptation is irresistible to start assigning probabilities to these events. And you want to be sure that if you assign probabilities to some events, you can assign probabilities to the other events that can be built out of them. So you don't get in a situation where you can say, I can assign a probability to this event and to this event, but I don't have a clue what the probability of their union is. So in an event space, we have a collection of events, a collection of subsets to which we are proposing to assign probabilities. Now, your first temptation will be to go a bit too far. Your first temptation will be to say, that means if I've got two events in this event space, I have to be sure that I can assign a probability to their union, that I can assign a probability to their intersection, that I can assign a probability to their difference, and that I can assign a probability to the complement of either of them. Then I'm sure that I'm safe. Well, you want to be able to do that, but mathematicians tend to be much more conservative. Mathematicians like to assume as little as they can get away with. So the first thing I want to show you is that if you can form unions and you can form complements, then you can also form intersections and differences. And therefore, we won't have to fuss about intersections and differences. So the first formula I want is a way that gets intersections when we use only union and complement. And I'm going to see whether one of you can think of this. I want a formula for the intersection of A and B that involves only the operations of union and complement. And if you challenged me to do this, the first thing I would do is the standard mental crutch, a Venn diagram. And I might actually shade in the intersection of the sets A and B. Okay, let's work on this. Has anyone seen a way to do it immediately? Yes.
The complement of the union of the complements.
The complement of the union of the complements. Great. So we take the complement of A, form its union with the complement of B, and then complement the whole mess. And I'll draw a couple of pictures to show why that's reasonable. Here's A. Here's B. There's the complement of A. There's the complement of B. And you can see that much of A got included here, much of B got included here. And in fact, when I take the union of these things, A complement union B complement, I shade in everything except that little bit, and when I take the complement, I've got precisely what I want. Which means if we have complements and unions, we can form intersections. That's a good start. In fact, that's the harder one. A take away B. This might be, for example, all Republicans except the ones that are in the House leadership. Can someone find a way to express this concept just in terms of unions, complements, and things we already know how to make out of unions and complements? Yes?
The intersection of A and the complement of B.
Very good. The intersection of A and the complement of B. That is, we want everyone who's both a Republican and a non-leader. Okay. So now we've got intersection and difference taken care of, and that means we can make some rules for an event space. So here are the rules for an event space. It includes the null set, which I'll denote by this lowercase v. It is closed under unions and complements. So that if the event space includes event A and event B, it also includes the union of A and B. We've proved, this is actually a rigorous proof, that it's therefore also closed under intersections and differences. Someone might say, well, surely you must include among these requirements for an event space that it includes the entire sample space. But I say, I don't have to include that in the rules. Why not? Because the entire sample space is the complement of the null set. So these are the only rules we need. So what's the smallest event space you can think of?
Null space.
No, that's not an event space because it's not closed under complements.
Oh.
Yes?
I'm sorry, what do you mean by closed?
Closed means that if an event is in the event space, the complement of that event is also in the event space. The set of all things that are in the event space but not in the given event. So my objection to the previous suggestion that the null set alone is an event space is that's not closed under complements because the complement of the null set is the entire sample space. So someone have another candidate for the smallest event space?
a given event and or a given individual case and its complement?
Jay has suggested an individual event and its complement. That actually wouldn't work for two reasons. One, it doesn't include the null set, and two, it's not the smallest.
Wouldn't it just be the set that included the null set?
Right. Set whose only member is the null set?
No, I've already said just having the null set doesn't give us an event space because that includes an event without including its complement. Now there's an easy fix for that.
Sure.
Somebody must have thought. Jerry?
Include the universal set.
Include the universal set. So this is the null set. This is the entire sample space, the universal set. This is rather trivial, but it is an event space. It's trivial because the probability of this is 0 and the probability of that is 1. Nonetheless, it is an event space, and you might be thinking, this is just plain stupid. If we're dealing with playing cards and the experiment is you throw them on the floor and ask a kid to pick some of them up, we want to include all subsets of this set of playing cards. Why would you want to consider anything else? Well, life isn't that simple. Here's what is now my current favorite example. Suppose the experiment is you go into the mystery section of the library, you pick a murder mystery at random, and figure out properties of the murder. Okay, well, one possible event might be the murder was committed by a man. Another possible event might be the mechanism used for the murder was poison. Another event might be the murderer was detected by a female private investigator. There's no way you can enumerate all the individual outcomes there. Nonetheless, it would be reasonable to say, in a randomly chosen American murder mystery, the probability that the murder was done by poison is these days only about 6%. So you want to talk about some events, and the important thing about event spaces is if you're talking about some of the events, you want to be sure that you can work out the probabilities for any events that you make out of those. So the smallest event space is rather trivial, but we can do some others that are smaller than all the subsets. And this is really interesting. And this is something that was, I believe, discovered in the 20th century. Probability is a fairly recent branch of mathematics. The axioms were formulated by Kolmogorov in Russia, I think, in the 1920s. So this is a much newer subject than calculus, even though certain aspects of it are quite elementary. And here is a lovely example. Let's look at subsets of the set consisting of 1, 2, 3, and 4. And let's make an event space. Event space A. No, I shouldn't use event space A. Well, I'll try to do this. Usually for event spaces, you use some fancy letter. So there's a fancy letter vaguely resembling an F. And this will include the following collection of sets. It's going to include the null set. It's going to include the set containing only 1. It's going to include the set containing only 2. Now someone tell me what else has to be in this event space. Has to be.
1 and 2.
The whole.
1 and 2.
1 and 2. The whole thing.
Yeah.
What else? 3 and 4, because that's the complement of 1 and 2.
3.
No, 3 doesn't have to be in there. There's no way that you can make 3 by forming intersections and complements of what I've got. So we can leave 3 out. And in fact, that's precisely my point. This is going to be an event space, but it's not going to be simply all the subsets of 1, 2, 3, 4. But there are a couple of others we have to have.
2, 3, and 4.
2, 3, and 4. because that's the complement of 1, and
1, 3, and
1, 3, and 4. So there is a reasonable example of an event space which is not entirely trivial, but which is not all the subsets of the given set. Now, here's the interesting thing about this. Let's make another one and call it G. And I don't want to do the whole thing because it gets rather tedious. But this time we're going to start with 1 and 3 and do the same thing. And I'm just going to say, etc. So this is an event space. That's an event space. And here's a really funny thing about event spaces. Let's take the union of these two event spaces and see how it starts out. Well, it's got the null set. It's got 1, 2. It's got 3. It's got 1, 2. It's got 1, 3. And it goes on. And who can see why this is not an event space?
Missing 4, which would be the complement of 1, 2, 3.
No, it actually doesn't have 1, 2, 3 in it. 1, 2, 3 isn't in this, it isn't in that. So all I'm doing here is listing all the events that are in this or in this. You're on the right track. There's something that's missing, but it's not the one you identified. Who spotted what's missing? Knowing that an event space includes these, who can see one set that would have to be in this in order for it to be an event space
1, 2, and
that is not in either of these?
2, 3.
2, 3, okay? Because an event space is closed under unions. So if this were an event space, it would have to include 2, 3. That's not here. That's not there. So event spaces have this surprising property that the union of two event spaces is not necessarily an event space. Okay, so now we've got the collection of sets, the collection of events to which we can attempt to assign probabilities. And let's see if we can formulate on this rather gray board some rules for this. So I'm now moving on to topic number 9 in the outline, called addition of probabilities. And I'm going to start by what Sturzacher calls the basic addition rule. And this is really simple. However, I can make some good use of it. I took some golf lessons last year, and my instructor said to the group of us assembled duffers, I can't make you hit the ball like a professional, but I can at least make you look like a professional. And he did his best. Same way. I can't turn you all into mathematicians, but I can make you look like mathematicians. And the first way of starting to look like a mathematician is to write that symbol for probability. In tech, this is \mathbb curly bracket p. This is the notation we're going to use for probability. There's a double line down on the p. And once people see that, they'll think you're a really great mathematician if you use symbols like that. What we're going to talk about is the rule for probability of A union B in the case where it's a disjoint union. We have events A and B whose intersection is the null set. So if you're thinking of this in terms of Venn diagrams, there's A, there's B. Someone want to propose a reasonable rule for the probability of the disjoint union of two sets?
Probability of A times the probability of B.
You're close. Plus,
Okay.
yeah. Probability of A plus the probability of B. If you have a pet, and I know the probability that your pet is a cat and the probability that your pet is a parakeet, I can calculate the probability of the event that your pet is either a cat or a parakeet because I am unaware of any creatures that are both cats and parakeets. The intersection of is a cat and is a parakeet is the null set.
I haven't swallowed a parakeet.
Okay. Now, I want to try extending this, and now this is really subtle because we're going to be getting into the infinite. I'm going to assume this rule only for 2 events, and now I'm going to try to extend it to more events. And what I'd like to do first is to extend it to a finite number of events, say the probability of A1 union A2 union ... union AN is equal to the probability of A1 plus the probability of A2 plus on up through the probability of AN. And I don't need to assume this is a separate rule because I can prove it. Who can tell the class what is the orthodox strategy for proving something like this? When you've got something for 2, how do you prove it for finite n? Yeah, Jerry?
Induction.
You prove it by induction. Now, one of the things you'll be expected to do in this course is crank out inductive proofs because they're very, very useful in this field, and they're easy to do, and it's a nice way of working into formal mathematical thinking. So, someone remind us, what do we need in order to do an inductive proof? What are the 2 ingredients for an inductive proof? Yeah, Robert, you got?
Yeah, you have to have the initial condition.
You have to have an initial condition or a base case. And in fact, this is a perfectly good base case. We're assuming that this rule works for 2 events. And then what's the other thing we need?
You need to assume that it works for n plus 1. If it works for n, you have to assume it works for n plus 2.
If it works for n, you have to prove
it
works. Exactly right. Okay.
There's an assumption, you assume n,
Yeah.
and then you prove n plus 1.
So the way an inductive proof works is you assume that it works for n, and you prove that it works for n plus 1. So let's do that. We want it for n plus 1. And I can put some extra parentheses there, can't I? So now I have the union, the disjoint union of 2 events. One, this union up through n, and the other one is just the event n plus 1. And by my rule here, I can say this is the probability of the left-hand event, and then I add on the probability of the right-hand event. And since you got us correctly down this road, tell us what I'm allowed to do with this now.
You assume that it's true. You've already
Yeah, exactly. I assume that it's true, so that I say I can assume that that's true and write it as the sum of the probabilities of the individual events.
Lo and behold, it is then the probability of n plus 1.
Yeah. And then I add on this one, and that's the result I want for the n plus 1 case. Okay, this proves it for all finite n. This means it's true for n equals 10, n equals 100, n equals 1,000, and remarkably, that's not good enough. So here's an example where it's not good enough. You go to a fortune teller, you're unmarried, and the fortune teller says, I'm looking into your future. The probability that you will meet the love of your life next year and marry her is 1/4. The probability that this will happen the year after next is 1/8. The year after that, it's 1/16. The year after that, it's 1/32. And by the way, as long as you're single, you're immortal. Okay, now you can ask, what's the probability that I will eventually get married? And you try using this rule and writing it down and say the probability that I get married is equal to the probability of A1, married next year, which is 1/4, plus the probability of A2, married the year after that, 1/8, plus the probability of A3, 1/16, plus dot, dot, dot. It never stops. Who can sum this series in his or her head?
It's a geometric series, and the sum is 1.
Nope. 1/2.
1/2, sorry.
We'll come back to this later. My favorite series summing story involves the two trains that are heading toward one another. The two trains are 120 miles apart. They are heading toward one another at 60 miles an hour. A bee flies off one of these trains. It flies over to the other train, back, back. And the question is, how far has the bee flown when the two trains finally collide? Going there, 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 there. And the story is that this question was asked of von Neumann, I believe.
Right.
And he thought about it for a while, a few seconds, and said, "Why? 100 miles." Of course, that is the obvious answer because the trains are going to collide after an hour and the bee flies at 100 miles an hour. He was told, well, your colleague, Dr. X, solved that problem 2 seconds faster than you did. And von Neumann looked and said, nonsense. No one could have summed that series that quickly. So some of you were able to sum this series quickly. We'll come back to geometric series in a minute. But the issue I want to raise now is, does this calculation follow from this rule? And the answer is no. So we need a separate assumption that the probability of a countable union, the union from I equals 1 to infinity of events A sub I, is equal to the sum from 1 to infinity of the probability of those individual events. Proving this for finite n by induction does not establish this. This is a central assumption of probability theory, and it's a controversial one. This is the orthodox view of probability. There are two unorthodox schools of probability, one of which says you never talk about infinite unions of events. You only talk about finite unions. That means the answer to this problem is it's not covered by my theory. Most people don't like that. The other school of thought is, why stop with countable unions? Let's go to uncountable unions. Like the probability that when you put your pen down somewhere on this board, calculate from that the probability that you'll put the pen down in some set of points on this board. This gets you into horrible mathematical complications and paradoxes. So we will stick with the orthodox view. We will assume that this rule works for countable unions, and even those of you who know what uncountable unions are, we won't talk about them. Okay, so now we got this basic formula, and we can say a little bit more about probability functions. Well, that one's dead. Good thing I bought 16 of these at Staples, so I should survive the term. So I've been writing down this function p, the fancy p. And if you want to look like a real mathematician, you say, this is a function whose domain is an event space. You write your event space with a really fancy F. And whose range or codomain, depending on who taught you pre-calculus, the set of values that can actually be assumed by this function is what? What's the smallest probability that you can have?
0.
0. And what's the largest probability that you can have? 1. So what is this course about? This course is about functions from event spaces to the closed interval from 0 to 1. And it's interesting. We're going to be able to spend a whole term on this and barely scratch the surface. What requirements do we want to put on this? Well, I would say the first of these requirements that I would list is this disjoint union property that I just mentioned. Probability of A union B is the probability of A plus the probability of B, provided these things are disjoint. I should say that while our textbook doesn't mention it, there are perfectly useful functions that have this property and not the ones that follow. An example would be you have a large stock portfolio. There are various subsets of your stock portfolio, and the function could be the function that assigns to any subset of your stock portfolio its change in market value over the last 24 hours. That can be either positive or negative, and it won't necessarily lie between 0 and 1, but it does satisfy this property. If you have a set of Australian stocks and a set of utilities, and you own no Australian utilities, the change in value of your utilities combined with your Australian stocks is the change in market value of your utilities plus the change in value of your Australian stocks, and both of those can be 0, positive, or negative. In order to get closer to probability, we add 2 more rules. The next rule is that no event ever has a negative probability. So a probability is greater than or equal to 0. There are lots of functions that satisfy these 2 properties that are not probabilities. For example, if you take regions on a map, and the function is the function that assigns to the region on the map its area, it satisfies this property. The area of Australia plus the area of New Zealand is the area of the country that would be formed if Australia and New Zealand combined into a single country. No country has negative area, but it's not a probability. In order to make it a probability, I need 1 more rule, and that rule is that the probability of the universal set, the event that's guaranteed to happen, is equal to 1. So that's what makes something a probability function. Now let's see what we can prove about this. I'm now into the second bullet under topic 10, and I do hope I remembered to say I was starting topic 10, probability functions. What I want to do is to develop a simple rule for differences. Let's consider the probability of B take away A in the case where A is a subset of B, and this notation would be represented in a Venn diagram by showing B with A included strictly within B, though it includes the possibility that A and B are exactly the same set. Well, let's first think about this in terms of the areas of these regions. Can someone see a simple formula for the area of region B if you take region A out from the middle of it? If you can see that, you'll have the right answer.
Probability of B minus the
probability of B minus the probability of A. Thank you, Jay. That's correct, but now we've got to prove it. And being mathematicians, in proving it, we have to use these rules. And the trick of doing these proofs, and you'll probably see one on your first quiz, is you have to rewrite things so that this rule applies. And here's a good way of doing this. Who can see how to write B in terms of A and B take away A? Yeah, Jerry?
It's the union.
It's the union, right? B is A union B with A removed. and this is a disjoint union. Everyone happy with this? This is A. This ring is B take away A. The union of the two is B, and this have nothing in common. They have a null intersection. And therefore, by our property of a probability function, P of B is equal to P of A plus P of B take away A. And now I just move P of A to the other side of the equation. Change the sign. General principle, when you have something like this that you have to prove with a minus sign in it, what you want to do is rewrite that equation so it has only plus signs in it, and then see if you can get it from the general principles. That works almost all the time. Okay, another property. So I'm going to have to erase this one. If A is a subset of B, then the probability of A is less than or equal to the probability of B. This is really pretty obvious, isn't it? If event B is you get a black card and event A is you get a spade, you say the probability of getting a spade is no greater than the probability of getting a black card, whatever your probability estimates may be. But how would you prove it? What's the missing term here? It's B take away A, right. So you can say the probability of A plus the probability of B take away A is equal to the probability of B, and this quantity is what?
Greater than or equal
it's
to
greater
0.
than or equal to 0. Great. And therefore, if I throw it out, I'm throwing away something that's greater than or equal to 0, and I can replace my equal sign by a less than or equal. Okay. Now I'm going to prove the most important of all of these rules. I'm going on to topic 11, the inclusion-exclusion rule. And I'll be devoting pretty much an entire class worth of material over the next 2 or 3 weeks to applying this very useful rule. Here's what it says. It says the probability of the union of A and B in general, when A and B are not necessarily disjoint events, is equal to the probability of A plus the probability of B, and then there's a correction term. You have to subtract off the probability of the intersection of A and B. This is probably about the single most useful rule in all of probability. And here is how we set about proving this. So I want to make a suggestion first.
Draw a Venn diagram.
We could draw a Venn diagram. Good start. So there's A. There's B. There's the union of B. And the trouble is that tells us a lot about the sets, but it doesn't tell us very much about the probabilities. Let's try writing the probability of A union B in terms of something we've already talked about. That's the probability of A plus the probability of B take away A. And this is not only a union, it's a disjoint union. So this formula is valid. That is, the union of A and B is the union of A with B take away A. Now what do you want to do with B take away A?
We just said that was probability of B minus probability of A.
That was in a special case.
Oh.
So let's look at B take away A. And let's form the union of B take away A with the intersection of A and B. Okay. Here's B. There's the A intersect B. This dotted region is B take away A. So if I take the union of B take away A, this part, with A intersect B, what do I get?
B.
I get B. And not only that, this is a disjoint union again.
Probability rules work.
So I'm being sloppy here. That's just B, and therefore the probability of B take away A plus the probability of A intersect B is equal to the probability of B. Okay, now we're there because all we have to do is to eliminate B take away A. So probability of B take away A is equal to the probability of B minus the probability of A intersect B. And now I substitute that in up here, and presto, the probability of the union of A and B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So I proved this just using my properties of probability spaces. Now I want to finish up with the last topic, which I've called many ways to skin a cat. This is a straightforward looking but surprisingly difficult problem that is a variant of one in just about every standard probability book. I started giving this in one of my undergraduate courses where the students were doing the lecturing, and I kept discovering that different students would come up with different and unexpected ways of solving this problem. And it turns out there are 4 quite different looking ways of solving this problem. And if you do them right, they all give you the same correct and not quite obvious answer. So here is the problem. I shuffle a deck of cards. I turn up one card, and then out of the remaining 51 cards, I turn up a second card, and the question is, what's the probability that at least one of the cards is a spade? And the answer is not 1/2.
No.
The way to tackle this problem is to identify some events. And so let's say event A is the left or first card is a spade. And event B is the card on the right. Second card is a spade. What's the probability of event A?
13 and
1/4, right? You know, if I deal out 2 cards and you look at just one, ignoring the other, the probability that you'll be looking at a spade is 1/4. What's the probability of B?
That changes depending on whether or not A was a...
No, it doesn't. Look, that's tempting to say, and I'm going to be getting into that sort of reasoning in a minute, but okay, don't look. Okay, now you can look. I covered one up. What's the probability that the one I covered up is a spade? Oh, no, that's... What's the probability that the one I covered up is a spade?
5, 12.
If you don't see this card, it's 1/4. You're quite right in saying that once you know something about the other card, the probability that the other card is a spade is now in general different from 1/4, but you have now stumbled across the concept of conditional probability.
So what you're saying here when you wrote event B, you're saying that event B happens completely independently of event A?
That's right. I'm saying
okay,
I shuffle.
Then it would be 1/4.
I shuffle the deck, and basically what I'm asking is, what's the probability that the top card on the deck is a spade? 1/4. Separate question. What's the probability that the second card on the deck is a spade? 1/4.
Did you put the first card back in again so that you're still working with the
No,
52
I
card
haven't
deck?
built anything off the deck. I'm saying I've shuffled this deck. The probability that the top card is a spade is 1/4.
Yep.
The probability that the second card is a spade, 1/4.
Yes.
The probability that the 45th card
Yes.
is a spade is
Yes.
1/4.
How about make it?
Don't you really have to emphasize that you don't know what the top card is
Yes.
when you make
Yeah,
the rest?
I'm asking the question. I'm asking the question about the 32nd card, independent of the rest of the deck, and the answer is 1/4 for each card in the deck.
Rephrase it, saying you're shuffling 2 independent decks. What are the one, and deck?
No, that would
turned it
make
over
things misleadingly simple because it's now going to get a bit complicated. I have to finish this problem, and so now I'm going to answer the question. The answer is 15/34, by the way, and I'm going to get it in 4 different ways before we finish up. Now, a comment: I get 2 one-hour tapes, and in past years, I've been quite scrupulous about trying to finish at 9:35, but I figure if somebody's got a trackless trolley to catch, you can leave and watch the last 10 minutes on the online version. So I will finish up this topic tonight, partly because there's a homework problem kind of like it. So here's what I have always thought is the easiest way to do this problem. Here's our Venn diagram. And I think the easiest way to do this problem is to say that the probability of A union B is equal to 1 minus the probability of the complement of this event, which, as you learned earlier on, is the probability of the event A complement intersect B complement. Everyone see this is a valid conclusion from our rules of probability. Now I'm going to do what you wanted to see me do. Let's calculate this. This is equal to 1 minus the probability of A complement intersect B complement, which means I turn up a card that's not a spade, and then having done that, I turn up a second card, which is also not a spade. What's the probability of turning up a first card that's not a spade?
3/4.
3/4. Okay. Now I have 51 cards left, and how many non-spades are in them?
51 minus 13.
51 minus 13, aka 38. So the probability of turning up a non-spade followed by a second non-spade is 1 minus 3/4 times 38 over 51. That's 17. That's 19. That's 2. That's 1 minus 19/34, or 15/34. And that, I thought, was the obvious way to answer the question. But there are 3 other ways to skin this cat. Here's a nice one. Say, look, you just proved this inclusion-exclusion formula. Why don't you use it? Okay? Approach 2. Probability of A union B is probability of A plus probability of B minus probability of A intersect B. That's 1/4. That's 1/4. You didn't like it, but now I'm going to fix it. What's the probability of A intersect B? That's the probability that I turn up a spade. It's not going to be a spade. And then promptly turn up a second spade. Okay. What's the probability that the first card I turn up is a spade?
1/4.
Okay. Now I have a deck with only 12 spades left. What's the probability of turning up a second spade? 12 over 51, which simplifies to 4 over 17. So this is 1/2 minus 1/17, which is equal to 15/34. Isn't that nice? Okay, at that point I thought, well, now I know both ways of solving this problem, until one of my students got up and said, I see how to solve this problem. The probability of A union B is the probability that you get a spade on the first card plus the probability that having failed to get a spade on the first card, you get it on the second card. And everyone see that from the Venn diagram? That's really very nice. It's saying that you've got A, and then you have to add on the probability of the intersection of B with A complement. Let's work that one out. P of A is 1/4. We've agreed. And now we have to add on the second probability. What's the probability that the first card I turn up is a non-spade? 3/4. Okay. Now, having turned up a non-spade, I have 13 spades left, but I only have 51 cards left. What's the probability of turning up a spade after I've turned up a non-spade?
13 out of 51.
13 out of 51. Now the question is, can I do arithmetic with fractions after 9:40 in the evening? I think so. That's a 17. And so what I have is 1/4, which is 17/68 plus 13/68 from the second fraction, which is 30/68 or 15/34. Okay, at this point, I thought I'd seen them all until my teaching assistant solved the problem. And he said, here's how you do this problem. Look at this Venn diagram. It's obvious. There are 3 regions, this one, and this one. And you have to add up the probabilities. The way you do this problem is the probability of A union B is the probability of A intersect B, that's the part in the middle, plus the probability of A complement intersect B, that's the bit over here, plus the probability of A intersect B complement. And the nice thing about this approach is these two probabilities are equal. So once you've figured out one, you know the other. And so probability of A intersect B, we worked that out a minute ago. That's 1/17. The probability of A complement intersect B, I just worked that one out here. That's 13/68. But I've got 2 equal terms. And when I add them up, I get 2/34 plus 13/34 or 15/34. This is a problem similar to this is the only really challenging one on the homework, which you can have fun working on. So go off, try the homework at 5:30 next week in One Story Street, as indicated in the syllabus. For those of you who are in town, Chris will be running a section. You can ask anything about the problems or anything else. And at 8 to 9 on Sunday night, get on to the bulletin board and ask your questions. We'll see how this works. Starting this week, you've got a problem set due next week. It's straightforward, but still a good time to get busy talking about it.